Welcome in this video describing the Arcadia method and the Capella workbench with an example. The example is a level crossing traffic control that is used by Jean-Luc Voirin in his Arcadia book. Jean-Luc Voirin is the main author of the Arcadia method. In this video, Jean-Luc will focus on the physical architecture, how the system will be developed and built in order to secure the subsystem specification and subcontracting. Typical activities in the physical architecture include the definition of architectural patterns, the integration of technical constraints, make team byte choices, and the finalization of the detailed internal interfaces.
Now, let's focus on the detailed view that will be detailed enough so as to specify to subsystem suppliers and, of course, to fully integrate, verify, and validate the system itself. So we go one step further. If we consider the different behavioral components in physical architecture, it will be built from what we have seen previously, but of course much enriched. Here is a view of the different components. So we have roughly here depicted the different logical architecture level components. Here, as you can see, we are much more detailed with some new components such as system operators interface, for example, separation of safety-related command and control component between major incident management and system status management, for example. Same way for the different railway facilities, we have different kinds of signaling elements with the train emergency stops, and we have some crossing prevention devices that we want to detail a bit more, and we will focus on that later. Of course, those behavioral components here have to be populated by functions, which are inspired from the logical architecture functions, but which are dedicated to describing the physical component behavior themselves. So let's have a look to them. Okay, this one looks a bit more complex. Here we've got the different behavioral components that we have seen, as you can see, but they are populated with the different functions that describe their expected final behavior. Okay, so we have, of course, the different component interfaces that have been described and that carry the different functional exchanges described at function level. So this is a global behavioral description. If we focus now on the way the behavioral components are hosted by physical resources, such as computing means and hardware devices and so, let's have a quick view on them. So this is now the really hardware view of the different hardware components here. So the control system cabinet, for example, split into two computer boards, hosting two computer boards, one which is dedicated to the procedures as standard ones, and one which is high availability because it deals with safety-related behavioral components here, as you can see. We have a set of signal management, for example, and all those signal devices have the same behavioral component, as you can see here. So we have two replicas of one single replicable component, which is the railway signaling capability. We have description of detectors and at different levels, and we have one lifting barrier that we will focus a bit more on later, and a crossing prevention device. Lifting barrier is what we usually see in level crossing systems and platforms. Here we have a stronger, as you remember, we have a stronger constraint, which was that we should prevent any vehicle to enter the crossing if it was not allowed to do so. So this is done by having a device that will physically prevent vehicles to enter the crossing by means of a liftable platform on the ground itself. So this will be studied a bit later. And we have another one, which is that for detection purpose on the track, on the level crossing, both road vehicles and trains detections, we need some detectors. Either we consider separated detectors, or we have the opportunity, and this is a physical design choice, to mix them into one single solution, which is a road traffic detection radar. This road traffic detection radar will be able to manage both detection on the railway track and detection of road vehicles on the track, on the level crossing itself, but also detect vehicles approaching the crossing and possibly vehicles stopped behind and on both sides of the crossing as well. So this one will meet different expectations in logical architecture of different logical components that can be merged into one single road traffic detection radar. Okay, just a look to man-machine interface. We have very little spoken about that up to now. We have just considered, as you will see, in logical architecture, that we had to interact, of course, with the operators. This was done that way. So this is a picture that comes from logical architecture. We have the different functions that are performed by the operators here in blue. We have the different functions that are performed mainly by the system control components, and we have some interactions between them. So the real operators to system interface is mainly expressed by those different functional exchanges between both. And this is sufficient at logical architecture level, because we don't need to go further there. This is perfectly sufficient to describe what each activity of the operators needs in terms of incoming information, and what kind of orders, commands, and information it has to send to the system. So at logical architecture level, it can be sufficient to describe it that way. The situation is different, of course, at physical architecture level, because here we have to deal with the components that will be in charge of providing the real human-machine interface in the architecture. So we have to go further, and this is done that way. Here you see the same focus with, roughly speaking, the same kinds of function on both sides, but we have added some man-machine interface functions that has to deal now with the real interactions and probably more details. As you can see, for example, here, we have decided to emphasize the fact that the traffic and the system situation will be displayed on a map, on a geographical map, for example. And we have, of course, displaying traffic and system alerts and processing operator commands as well. And those information are routed towards the appropriate system functions that have to deal with them, or that are able to deliver information for the operators. As you can see, this is the way to describe in more details what is expected from the man-machine interface component, and so as to specify it, and this will be allocated to the appropriate behavioral component and resource implementation component that will deal with building the interface. Now let's have a look to the lifting barrier architecture. This is a way for us to introduce some representations we are not necessarily used to manage, such as some kinds of electrical or electromechanical devices, or, as we will see, hydraulic ones. The architecture of the lifting barrier is interesting for that. Here is the architecture of the lifting barrier. If we just declutter a bit it, as you can see, we have a control board, an electronic control board, an electric motor, a mechanical transmission, and the barrier itself. It's just one single barrier here. And of course, we have to exchange some kinds of commands from the control to the motor. Here, the motor will just drive the barrier command, and we will have a detection of the barrier position based on the rotation angle delivered by the mechanical transmission, and we will have a signal of blocking, of barrier being blocked, for example, toward the command control so as for it to stop its command here. So as we can see, we have a clear distinction of the physical real implementation component, so electric motor, mechanical transmission, and the behavior which is expected from them. So for example, generating motion, but here as well, both commanding the barrier and detecting the position of the barrier, for example. If we add now functions, as you can see, we have a set of elements that will describe what is expected from each behavior. So for example, the electric motors, when generating motion, will transform an electrical energy voltage into mechanical torque, and he will therefore deliver a torque to the mechanical transmission. And of course, this is a standard behavior of an electric motor. He will have to modulate the intensity of the command on the electrical power according to the set point and speed which is imposed by the mechanical transmission. So the mechanical transmission has a reply to the torque, the rotation speed, which is allowed by the load, the mechanical load that it has to face. So as you can see, we can describe things which are not data interactions, but just physical interactions as well, for example, and it looks not so badly adapted to describing this, as you can see. Here again, we have in the barrier command the reduce speed and increase torque, which is the first version function expected from the mechanical transmission, and of course, therefore, activating the barrier with torque and rotation speed here again, and we will have here the position of the barrier that will be commanded by this mechanical transmission. If we could focus now on the crossing prevention device, so as I mentioned, it is complementary to the lifting barrier. Its role is to physically prevent a vehicle to enter the crossing if it is not allowed for so. So the idea is that we will have an hydraulic system that will raise an obstacle on the ground so as to prevent vehicles to enter the crossing. So how does it look like in physical architecture? Here again, let's remove functions for the moment. So we have, as you can see, the same kind of control board. We have decided to reuse it, so we have created a replicable element, a control board which is replicated both in the barrier and in the crossing prevention device. But of course, the kind of command that the hydraulic system expects is not the same one. This is what we have defining a kind of adapter that will be in charge of convert the command, which was just a one single command, into a separation between locking and opening commands, because this is the way the hydraulic system works here. So we have this adapter converter with its own housing, and we have the description of a regular standard hydraulic system with its pressure generator, pressure and flow rate regulation as well, and control, distribution towards different actuators, which are in fact hydraulic cylinders, and that will command the different ground obstacles and check for their positions as well, and which will be sent back to accumulator. So as we can see, we have the standard synopsis of an hydraulic system here with the different pipes and hoses that transport the different streams of hydraulic liquid, for example. If we display functions now, we can see the same ones here as expected. The conversion, which is done by the adapter, and then as you can see, we will have mainly a fluid under pressure that will flow all along the different subsystems with different functions, such as managing pressure regulation will be done by diverting part of the fluid toward the accumulator. Reducing pressure on request will also be done that way. The flow rate control will involve filtering impurities and maintaining a constant flow rate, and so on. The dispatchers will direct the fluid toward the different multiple receivers that will convert hydraulic energy into motion and activate explicitly the different ground obstacles and so on. So as you can see, it's also perfectly possible at this engineering level to have a fairly high-level description of an hydraulic system as well as a purely electronic one, for example. If we go further into discovering the description of the crossing prevention device, we have here a description of the electric fluid which is transported in the different hoses that we have seen. Here, for example, we have an hydraulic fluid which is described as usually by its type, viscosity index, minimum or maximum acceptable temperatures, and possibly standards to which it has to comply. And of course, this fluid, which is the same one carried everywhere in the system, will have a different status depending on the system place. It will be high or low pressure, for example, so this will be depicted by a fluid status describing its current pressure and temperature. This is grouped into one fluid under pressure exchange item that will be carried all along the different exchanges that we have seen here. Now let's have a look to the road traffic detection radar. This one is a bit different, and it will be a way to go into a bit more details in describing interfaces between different elements. And here we will choose the traffic detection radar so as a support to illustrating those interface definitions and elaboration. So for example, if we consider the functional exchanges of the road traffic detection radar, here they are. Here is the detection radar with road detection and detection of vehicles on the track, and of course integrated test, and we have a set of information that are sent towards the command and control here. So the different information about the different vehicles, information about the system health and situation and operation here, and some information about, for example, a vehicle stopped on the track. As you can see, a detailed level choice of design is that it will be done by just checking that each vehicle who entered the crossing will be passed. If not, then it is likely to be blocked on the road itself, for example. So this, as you can see, this is a matter of low level of detail describing all the detailed information to be managed in the interface between the radar and the rest of the system. If we go to the different behavioral exchanges now that will summarize those different functional exchanges, we can see here those different ones, and we have just road detections and detections on the track, which summarize those different information sent from the different functions here up to the rest of the system. And going on in this description, here is a bit more physical view with implementation components as well. So we have here the different hardware components here, and we have especially focused on the way it communicates with the rest of the system by means of an Ethernet network through a router, which is described here. So as you can see, we've got the router. We've also got the physical links, which are Ethernet cable that connect the radar to others. And we have also defined what we call physical paths that show which of those physical links each behavioral exchange follows so as to provide information as expected. Here again, we will describe the radars similarly with an interface which describes all the data around it as is, such as its one, for example, where we have all the details of information delivered by the radar regarding presence of vehicles on the road. So those vehicles which are approaching, those who are stopped, has lists of vehicles describing their speed and their distance from the crossing. This is one benefit of using a radar rather than static detectors. And the side of the crossing on which the vehicle stays, and the hour of detection and the number of vehicles as well. And these are the different services or messages that are exchanged between the radar and the rest of the system as well.